So our project is has two different components. First main one is in scientific cosmological simulations led by Michael Norman. He was unable to make it today, so I'm speaking. And the other component is for software development, for developing the next generation of our software. So we use Enzo, which is for unigrid or uniform level. It works well at petascale, but adaptive mesh refinement does not scale as well. So I'm developing the next generation Enzo-P, which is parallelized using Charm++ and uses a scalable array of octree adaptive mesh refinement, which is in a separate framework called Cello. And I'm using Blue Waters for doing performance testing and optimization. So a little bit about Enzo. It's a very capable astrophysics cosmological application. It does hydrodynamics, self-gravity, chemistry and cooling, star formation, MHD, and radiation. And for each of these physics components, we have one or more numerical methods. Have a modified PPM for cosmology, a multi-grid and FFT-based gravity solver, several cooling and chemistry libraries and methods. And underlying these numerical methods are the data structures, particular structured adaptive mesh refinement, where each patch contains fields and or Lagrangian particles. So you can do field methods, particle methods, or combinations of the two. So the primary limitation of Enzo's AMR is it started in the 1990s when massive parallelism meant like about 100 processors. But today we have over 1,000 times that now. See, my slide is even dated. And this growth in the supercomputer sizes has affected these different components differently, the physics, numerical methods, and data structures. Physics is essentially the same. Numerical methods in Enzo are still mostly viable, but the underlying data structures are the main reason Enzo's scalability is limited. So this motivates the design for a more scalable AMR. So the idea is to keep the physics and many of the numerical methods and then build that on top of a separate scalable adaptive mesh refinement framework. So just to summarize the differences between the two, Enzo uses structured AMR, so you have patches of various sizes and shapes of increasingly refined resolution. It has communication patterns are both neighbor-neighbor and parent-child, and it's parallelized using MPI and also OpenMP threading. Enzo-P Cello uses an array of octrees, so each block has a fixed shape. The communication is neighbor only, except in some cases, because all the data lives on the leaves of the octree. And it uses Charm++ for parallelization. Just a brief overview of Charm++. Charm++ program is a C++ program in which you can have some objects are parallel tasks called chars. They're defined by having entry methods, which are methods that can be called remotely and asynchronously. And communication between these chars is via the parameter list to the entry methods. Underlying these chars is the Charm++ runtime system, which handles mapping chars to processors, scheduling entry methods for execution, and load balancing the chars. And Charm++ has multiple additional features, including checkpoint and restart to disk or double in memory, sophisticated load balancing strategies, and fault tolerance. So the main advantage of Enzo-P's scalability is how it does the memory usage. And that's the main limitation in the current Enzo. In current Enzo, the structured adaptive mesh refinement mesh topology is replicated across each MPI task. But in Cello, the AMR hierarchy is fully distributed thanks to Charm++. And there are some other modifications that I've tried to make. Let's see. Okay, so the way it proceeds is you do some computation on a block, and then you send your face data to your neighbors that will need it in the next cycle. And then you stop and wait for your neighbors to send their data to you. And then when you finally get the last bit of the ghost data, then you can proceed to the next computation. So this Charm++ enables a data-driven execution. And in Charm++, you usually do over decomposition, which can help with overlapping communication and computation. Let me skip some of the details. So I did some scaling tests of what we have so far, of what we've done recently. So this is a very basic test problem where you have an array of set-off blast-like problems, one per core. If you do that, then the mesh refinement kicks in in lockstep. So to have some variation, I changed the spheres into letters for the fun of it. I had some animations of this letters blowing up, but I was technical difficulties. Couldn't do that. So I recently added particles, so I wanted to test the scalability of that. So I did tests with hydro tests, just strictly hydro, and with tracer particles. And I've done runs up to 256 floating point cores and problems up to about 1.7 trillion cells for the just field data, or 0.7 trillion cells plus 0.7 trillion tracer particles. And that turns out to be about 50 million octree blocks. And each block is 32 cubed or 24 cubed. Now this is totally not able to be run on the current Enzo. You would require about 72 gigabytes of memory just to represent the AMR hierarchy, just the metadata. So I did some tests, and they didn't really look too good at first. So you see this turn down in efficiency on the left at about 1,000 cores. And when you look at different components, you see that there's something going on when it's doing communication. So I used the projections analysis tool that comes with Charm++, and it was relatively easy to identify just where the problem is, if not how to fix it. So I looked at bytes received and messages received in time. So you can see a characteristic flattening off which shows that it's reaching some bottleneck. And for the message, it's totally flat for the messages received, which indicates that it's the number of the overhead associated with a given message, not how much data is being transmitted. And at the bottom is a trace of a few of a 32,000 core run of a refresh. So you can see the different sizes of entry methods, which is totally to be expected because I'm doing corner data, edge data, and face data. But you see that in between, the white space is very regular. So to me, this indicates that there's some hidden order N or order P like overhead associated with the entry methods here. But fortunately, it was easy to get around if you just run it in SMP mode, Charm++ SMP mode. So I ran on 15 out of 16 cores for each node, so the efficiency on the left should be down like 15 over 16. But it's totally flat, and this goes out to 256,000 cores, floating point cores. So and there's no sign of it really starting to go bad like it did here on the right. So I'm confident that that scales well. Recently, as in last week, I finished implementing a gravity solver. This is so far just for uniform grids, but it's a component of our AMR gravity solver. So I did some scaling tests with this, and got something like this. We have on the left weak scaling, on the right strong scaling, and this is with the same data. And this to me looks to be pretty good. I haven't analyzed it in detail, except for this one data point at 128 cores, which is 2 to the 7, the red one at the top, which is kind of sticks out there. And I reran it, and I get the same thing. So it's, I can use the projections tool and see if I can track that down. So in conclusion, we are developing the next generation of ENZO parallel AMR cosmology and astrophysics application. The hydro scaling with particles, at least on simple problems we've tried so far, has been excellent through 256,000 floating point cores. The uniform grid gravity looks to be very good through 64,000 cores that I've tested so far. I just haven't gotten anything through the queue yet, anything larger. And the debugging of the AMR gravity is, I should get that going pretty soon. And so the next steps will be to analyze and optimize the uniform grid gravity, test and optimize the AMR gravity once that's working, and do more rigorous and realistic scaling problems. The ones I've done so far are just very simple problems that don't exercise a lot of the adaptivity and load balancing aspects. And that's all. That's it.